Look at this transaction stream. What you are seeing is a microservice processing millions of financial logs, suddenly gridlocking at 100% CPU utilization. The root cause of this failure is rarely the hardware. It is an algorithm relying on brute force nested loops and redundant sorting passes to parse the incoming data. A senior engineer looks at this bottleneck differently. Instead of recalculating the exact same data points over and over, they eliminate redundant computational work entirely by intelligently caching the system's state. On this system architecture dashboard, we can isolate the 3 specific computational targets causing the overload: subarray analysis, next greater logic, and top case streams. These targets map directly to 3 strict design patterns that intermediate developers frequently stumble on during technical interviews: prefix sums, monotonic stacks, and bounded heaps. For each of these patterns, we will diagnose the failing before state, map out the mental model required to solve the problem, and evaluate the mathematical Big O performance upgrade. Mastering the strict Java implementations of these 3 structures is the precise difference between writing ON² prototype code and deploying an ON production-ready architecture. Let's start with subarray analysis. The goal is to find contiguous blocks of numbers within an array that add up to a specific mathematical target. The immediate instinct for most developers is to deploy a sliding window, expanding and contracting a bracket over the numbers to track the running total. This diagram illustrates exactly where that approach fails. Watch this sliding bracket expand over the array 3, 4, -5, 2. As soon as the pointer hits a negative number, the window's sum drops unpredictably. The state is no longer strictly increasing, and the logic of the sliding window breaks down entirely. To handle fluctuating values, you drop the window and use a prefix sum combined with a hash map. On the right side of this split screen, we have a ledger. Think of a prefix sum exactly like tracking your bank account balance over a week. You do not need to pull every individual receipt to know how much money you made between Monday and Thursday. To find if a specific subarray equals our target K, we do not recalculate the entire array. Instead, we take the current balance and subtract K. If that resulting number exists anywhere in your historical hashmap ledger, it mathematically guarantees that a valid subarray exists, ending right at your current position. Translating this exact mathematical trick into Java requires knowing a specific fundamental hard truth about properly initializing your system state. In this code snippet for the prefix sum pattern, notice the glowing line. You must always initialize your hashmap with the key value pair of 0 and 1. This pair represents the fact that before you process any numbers, your running sum is exactly 0. Skip this step, and your algorithm will silently miss valid subarrays that start from the very first index. By caching the running tally in a map, you replace an expensive nested loop recalculation with a single-pass O of n historical lookup. The second structural bottleneck involves next greater logic, commonly seen in problems asking how many days you have to wait until you hit a warmer temperature. This horizontal array displays the naive approach. A pointer sits on day 1, while a secondary scanning line painfully checks every single future day to find a higher value. This creates a massive O of n² drag on the CPU. The solution is to defer resolving these queries by using a monotonic decreasing stack. Here is the stack acting as a vertical staging area. The strict rule of this structure is that every element dropped onto it must be smaller than the one beneath it, stacking neatly in descending order. The system holds these smaller elements in a pending state until a larger element, a warmer day, arrives and violates the rule of the stack. When that larger element hits, the smaller elements currently stuck on the stack instantly recognize it as their next greater value.
They record its position and pop off the stack in one continuous sweep. To execute this accurately, the stack does not actually hold the temperature values themselves. It holds the unresolved array indices, which is what allows the system to calculate the physical distance in days. Moving to the implementation, there is a critical Java-specific trap to avoid when you are building out this architectural data structure. Looking at this side-by-side comparison, you must never use the legacy java.util.stack class. Instead, always instantiate your stack using ArrayDeck. The legacy stack class is synchronized by default, adding massive, unnecessary performance overhead to every push and pop operation. ArrayDeck is the required modern standard. A monotonic stack achieves O of n performance because it keeps data in a deferred, unresolved state until a single larger trigger resolves multiple elements at once. Our final bottleneck involves tracking the largest or smallest elements in a continuous flow of data, known generally as the top K problem. Look at this massive array representing 10 million items. Calling a standard sorting algorithm to find just the top 3 elements forces the system to sort all 10 million data points. The loading bar shows the O(n) log n time dragging on just to identify 3 single integers at the very end. To fix this, bypass full dataset sorting entirely by using a priority queue configured as a bounded min heap. The logic here feels counterintuitive. If you want to keep the absolute largest elements, you actually have to use a min heap. Think of the heap as this velvet rope enclosure with a strict capacity limit of size k. It currently holds exactly 3 items. When a 4th number block tries to enter, the capacity is breached. Because it is a min heap, the structure instantly identifies the absolute smallest number inside the enclosure and immediately ejects it. By continuously letting numbers in and kicking out the minimums, the structure is mathematically guaranteed to only hold the maximum values, and the number sitting right at the top of the heap is your exact kth largest element. Structuring the data this way creates a massive leap in processing efficiency. Watch the equation on screen. By capping the heap at size k, the insertion time drops from the standard O of n log n sorting time down to O of n log k. If k is a small constant, that equation visually shrinks down to run in virtually linear O of n time. By enforcing a strict capacity bound, a min heap dynamically filters a data stream in a single pass, completely bypassing the need to sort the full dataset. While prefix sums, monotonic stacks, and bounded heaps solve very different problems, they share one strict underlying architectural principle. This diagram pulls together the ledger, the staging area, and the velvet rope. Notice how the glowing vectors from all 3 converge into a single pulsing node. That node is strategic state management. These are the exact triggers you need to internalize. If a problem asks for subarray sums and the array contains negative numbers, deploy a prefix hash. If the system needs to resolve next greater or next smaller queries, build a monotonic stack. And if you need continuous top K tracking without sorting the entire pipeline, bound a min heap. The core philosophy linking them together is simple. Advanced algorithms always trade a small, highly controlled amount of memory overhead to cache state. This immediately eliminates the need for redundant nested loops. I challenge you to benchmark these 3 patterns in your local IDE. Specifically, run a massive dataset through ArrayDeck and compare its execution time directly against the legacy stack. Passing senior-level interviews and writing resilient production code do not depend on knowing how to loop over data faster. They depend entirely on knowing exactly how to manage its state.